All right, ladies and gentlemen, this is your rotational motion concept map. This is basic overview for this first video, and then following videos I'm going to really unpack some specific examples, taking FRQs and things like that, and walking all the way through them and not skipping any parts. This is not a video for learning, this is a video for refreshing and reviewing. So the first thing I'm going to do is talk about torque. And so torque is calculated by FR sine theta. So if we go into the linear world, we look at linear components and you're able to convert them into its rotational components. I'll get to that a little bit here in a second. But when it comes to torque, you can think of torque as it's a force acting around a distance. So force around a center point. Something causing something to spin, or in some cases not spin, but the object itself is rotating. This is not circular motion where an object is in orbit or an object is rotating around another object. This is the object itself is spinning. So the first thing we do when we look at torque, it can kind of go in one of two directions. Either the torque on an object, the net torque on the object, does not equal zero, or the net torque on the object equals zero. So kind of the same thing when you look at dynamics way early in the year, if an object is accelerating versus if it's static. And so we're going to call this static or constant velocity. All right, and then this one is going to be accelerating. Now, it's going to be not linear acceleration, but angular acceleration, and I'll unpack that here in a moment. So, when we look at if T net does not equal zero, what does that do for us? Well, if the torque net equals zero, the first thing we're able to say then is that the torque clockwise on an object equals the torque counterclockwise, or the torque going to the left is equal to the torque going to the right. And so a wonderful example here is if I have a meter stick on a fulcrum and the torque that is causing it to go one way, let's use yellow here. Let's do green actually. So the torque causing this to go to the left or counterclockwise is equal to the torque that's causing it to go to the right or clockwise. Okay. Then what you're going to do then is break it into its components. And so if we only have one force, it would be force 1 R1 sine theta equals force 2 R2 sine theta. Now, this angle here can be a little difficult to get at as far as what angle do you actually measure. And so if we were looking at an object where the force is pushing directly downwards versus inwards at an angle, and then the last one pushing outwards at an angle. Now, there are multiple ways to do this, but the way that I teach this in the class, that way we all stay with the same thing. You're going to look at from where the force is coming from and towards your center point. So we're looking at this angle right here. So this is going to be your theta in all three of these examples. Now, since you're using sine, sine at one point will start to repeat itself, but I don't get into that too much. All I'm going to say is you take the angle from the force towards your center of motion. And we're calling the pivot point here on all three of those. Okay, so next thing we do with that is often these kind of questions, you're going to start off with saying if an object is static, meaning not moving, then the object torque counterclockwise equals torque clockwise, and then you go from here saying torque net equals zero. Now there is another example of something already spinning at a constant velocity. Let's unpack that one, and then I'll go back with the other one. So what if an object is already spinning, and it's going to be spinning at a constant velocity. What we then say here is that the net torque on it equals 0, right? And with that, we then also say that your angular acceleration equals 0. And then that's pretty much all you need to know when it comes to those. I really don't see questions like this pop up too much. When it comes in object rotating, I often see a fulcrum with a more like a meter stick balance kind of situation, this kind of situation. What I do see with torque net not equal 0 is when you get some other interesting things happen. That's when you go into an object that is spinning and it's speeding up. So if it's torque net does not equal 0, that means it's accelerating, but it's not a linear acceleration, it's an angular acceleration. So then we say that the object, it's spinning, it's going to be increasing its spin either in the clockwise or counterclockwise direction. And then that's when you take your torque net, solve for whatever you're going to solve for. And I'm going to unpack this example later on in subsequent videos. But that's going to be I alpha, where I is your moment of inertia, called your center of mass, moment of inertia. It's called a bunch of other things. Moment of inertia. So basically, that I value is, since it is spinning, we cannot use mass. We have to do this thing called moment of inertia. Maybe in a follow-up video, I'll unpack that moment of inertia. But really, all you need to know is this I value is given to you. You're not expected to memorize any I values ever whatsoever. It's always given to you. It's just simply a plug and chug at that point. They'll often just say moment of inertia or the center mass of the object is blank. Use it appropriately. And then angular acceleration is alpha. Alright, as far as this goes, I'm going to have an unpack video where I unpack this question a whole lot and really pull it out. And this is where you're going to see different types of questions like, this is where you have your pulleys. You often see your beams rotating. All right, this is where often the object is then hit into a spin or causing it to do something like that. Whereas these other ones are balancing. Another example that I have seen this pop up on, and I'm definitely going to do a video on, is, let's do another example down here. And let's call this a beam hanging off of a building, and then looking at the rotational components of this building. So since this force is acting at a distance away from its center where it wants to rotate, this turns into a torque problem as well, and so this is considered static. All right, I'm going to definitely have a video pop up later on about how to unpack both of these kind of problems. However, but we're moving on. All right, what if we go back to torque not equaling 0, net torque, and net torque equaling 0? Let's go with some more examples there. Oh, I did that wrong. There we go. Net torque does equal 0. When it comes to the terms of momentum, so if we go back and we search in our heads, linear momentum is mass times velocity. If we change this into its angular components, linear momentum is often denoted as rho. This turns into L. Mass turns into moment of inertia. We already talked about that. But then V turns into angular velocity, or omega. So if torque net equals 0, what you're then going to say is very, very easy stuff. So back when we say F net equals 0 on an object looking at collisions, we then very typically just start off with saying momentum before a collision equals momentum after a collision. if there is no torque acting on the system. So a good example here is we often talk about a ballerina spinning, and they hold their arms outwards and bring it inwards. Where do you unpack this? And so I'm going to try to let's do a stick figure here. So we got a ballerina spinning and their arms are out far versus the ballerina spinning and then they bring their arms inwards. What does that do to their I value? Well, as they bring their arms inward, it becomes easier for them to spin. So to go from a larger radius to a smaller radius, you're going to see that I value is going to decrease. So if we unpack this, we then say the center of mass before the moment of inertia before, angular velocity before equals moment of inertia afterwards, angular velocity afterwards. Now, often most of these values are given to you, and so it just simply turns into a plug and chug, but here's where some things start to get tricky. What we then notice is, for this example right here, let's do this in red. What we notice is that since their moment of inertia goes down when they bring their arms in, they're going to be spinning faster because their angular velocity has to go up, because what is over here is constant. Now, what I have seen a couple times is this turns into a kind of a linear question, like if she's holding a tennis ball in her hand, how fast would the tennis ball be going? Well, if we're looking at the linear velocity there, what we can then do is take this and convert it into its linear components. So we can say then is, we start off with the same beginning things, and then we convert this into its linear components. So you can take any angular components and convert to the linear components if you know how. At the end of this video, I'm really going to unpack and do every single one of those. Alrighty, now that is if torque net equals 0, meaning there's no work being done on the system, no impulse, nothing like that. That is, the momentum before equals momentum afterwards, because angular momentum is conserved. Now, if torque net does not equal 0, what do we then turn into? This turns into a work problem. And so then what we can't say is that the angular momentum before does not equal the angular momentum afterwards, because there was an impulse. There was a change in angular momentum. Kind of the similar way of looking at linear momentum and delta P being the change. So F net delta T. So since the change of linear momentum is impulse, the change of angular momentum is an angular impulse. And so what you have to then do is then plug this into a work situation, saying that the work being done is force dot distance, and then going on and going from there. And so either the situation is going to be that your total energy to begin with, so your energy total is going to increase, or summation of your energies is going to decrease. So for example I say if I'm spinning and then somebody comes by and slows me down, they're putting a torque on me for some time interval, for some distance, and then that is then causing my total mechanical energy to go down. Or if I'm spinning and somebody starts pushing me along, we're going to increase that total energy and go from there. So if I were to then take this and put it into linear components, well, what is the angular component of force? And that is torque. So torque net delta T. Okay, I'm going to do an example problem where I kind of unpack this and looking at how does angular momentum change. And usually this kind of problem is, there's a beautiful problem, and I'll do this one, where a ball hits a beam and causes it to spin. What is the angular velocity of the beam after it spins? Okay, so keep your eyes open for that example. I just don't have time in this video because I want to keep this video relatively short. All right, moving on. Surprise, surprise. Let's continue on saying torque net does not equal 0. And torque net equals 0. Oh, I did it again, folks. There we go. So let's unpack it. If this is accelerating over here, and this is not accelerating, now let's talk about it in terms of energy. So let's look at, if we look at energy to begin with, linear energy, gravitational potential energy, MGH, this really doesn't change in this. So you really won't, there's no angular components to it. However, kinetic energy does. So we've always done kinetic energy equals 1/2 mv squared. What about the energy of it rotating? So we call this K rotational. And that is 1/2 mass turns to I, velocity turns into omega squared. Alrighty, let's move on. So if it is not accelerating, that means the total energy initial equals the total energy final. Energy is conserved. So an example of this would be a ball that's rolling down a hill. Now before we would just say, that, the gravitational potential energy would then equal the kinetic energy at the bottom. However, since this is a ball, not only is it going to be going forward in a linear sense, but it's also going to have some rotational speed to it. And here's where you then, what I've seen these kind of problems do is, you then take this and you expand it. So then, gravitational potential energy would be mgh. Kinetic energy, linear kinetic energy, 1/2 mv squared. Rotational energy would be 1/2 I omega squared. And depending on what kind of ball we have, whether it be a full ball or an empty kind of shell, your I value would look different here. So you'd have to plug in 1/2 mv squared plus 1/2 the I value. Let's do it for an empty cylinder because I know that one offhand, and that's going to be mr squared. This omega, we can turn it to its linear components and say velocity divided by radius squared. And so what we've done is we've taken that problem, which is a pretty simple energy problem, back in energy, but when you add the rotational part to it, you have to expand that and then put it all in linear components, and then you can solve from there. Okay, that's it. As far as energy goes, energy is conserved. Potential energy beforehand turns into 2 types of kinetic energy afterwards. To make sure we really understand this, though, we got to look at what happens when the system is accelerating. And so then what we say is that the total sum of the energies initially is not the same as afterwards. You're going to see that change in energy. And so what we're going to do here is then have to calculate how much your energy has changed. And that based on your situation, it might change differently. So, if an object is, not spinning, you then, say energy initial equals 0, and then a torque acts on it for some distance. So torque net does not equal 0, and, for some distance, or for some theta. So let's say that does not equal 0. We then just plug this into our energy formula saying that the work being done on it, let's do, this kind of work, would then be equal to, let's say, K final. And so this would be, torque for some distance of theta. K final would then be, your K rotational final. So that'd be 1/2 I omega squared. That's an example of what that kind of looks like. I really don't see them unpack this too much, but there could be a rotational energy question looking at if it's accelerating or non-accelerating. Alright guys, before we wrap up this video, we're going to now look at how do you take all of your linear components and put it in angular components. So what we got is, we have just generally how to go from translational to angular components. Let's use a different color. So overall, for almost all of these, when you look at your kinematics, you can take your angular, and that's going to be its linear over radius. So for distance, your theta is going to be displacement over r. Your angular velocity is going to be linear velocity over r. And angular acceleration equals, linear acceleration over r. What this does not mean, angular velocity is not the same thing as centripetal velocity, and angular acceleration is not the same thing as centripetal acceleration. Not the same thing as angular acceleration. They're really easy things to mix up. Another thing is force. We're kind of taking this one and knocked it on its head. So force turns into torque. So torque equals Fr sine theta. That's how you're going to convert from force to torque. We can then knock this off and pretty it up a little bit and then say, torque equals F times R if that angle is 90 degrees. And then let's move down just a hair. Let's look at momentum. Linear momentum is mass times velocity, so angular momentum is I omega. And then impulse, delta P equals F net delta T. So change in angular momentum is going to be torque net delta T. And then the last one, when you look at energy, this one gets a little bit of different formulas overall. Potential energy is still going to be mgh. Linear kinetic energy is 1/2 mv squared. And rotational kinetic energy is 1/2 I omega squared. So as far as being able to do this well, you need to have a good foundational in first semester kinematics, dynamics, and energy, and then just applying it in a rotational sense tends to be okay. What I'm going to do is I'm going to do a focus question, really unpacking each one of these, and they're going to be connected to this YouTube video. So just sit tight, and soon it'll automatically play the next video. I'll see you next time.